Okay. So we'll talk about the rules for definite integrals. We will define what the average value of a function is. I'll mention the mean value theorem for integrals. There are two mean value theorems, one for derivatives and one for integrals. And then I'm also going to mention the fundamental theorem of calculus part 2, not because I want you to know that theorem as you read here today, but because so many people ask about it. They're like, how do you do this? Well, it's a pretty simple procedure for calculating a definite integral by hand. You just haven't seen it yet. So I want to just have you take a look at that. Hopefully we'll get to it today. All right, a couple of points to ponder. The variable of integration doesn't matter. And here's what I mean by that. Last week I showed you the integral from 0 to 1 of x to the 5th dx, and that turned out to be 1/6. Now if I said, what's the integral from 0 to 1 of t to the 5th dt? Same thing, 1/6. You can use any letter you want when you integrate. So long as I have the variable x and I tell you I'm going to integrate with respect to x, we're fine. Use any letter you want. Second thing to keep in mind, and always keep this in mind, a definite integral is nothing other than a number. So the integral from 0 to pi of the sine of x dx is nothing more than a fancy way to write the number 2. I can think of a billion different ways to write the number 2. 4/2, 6/3, whatever. It's just another way of writing the number 2. Okay. The integral from a to a of f of x dx equals 0. If the upper and lower limits in a definite integral are the same number, the value of that integral is 0. How come? You're talking about the area under a point. There's no area under a point. Rule number 2. The integral from a to b of k times f of x dx turns out to be k times the integral of a to b of f of x dx. What's the name of this rule? Oh, come on. It's the constant multiple rule for integrals. We had a constant multiple rule for limits, constant multiple rule for derivatives. Of course, there's a constant multiple rule for integrals as well. You'll find in a lot of instances it's much easier to pull the constant out front. So the integral from 0 to pi of 6 times the sine of x turns out to be the same as 6 times the integral from 0 to pi of the sine of x dx. And the value of this definite integral then would be the inner part is 2, the outer part is 6. And if you think about it, to find the area under a curve, we cut it into rectangles. And then we multiply the width of the rectangle by the height of the rectangle. What transformation does that 6 do to the sine wave? It'll stretch by a factor of, so didn't every rectangle just increase its height by a multiple of 6? And if you multiply the height of a rectangle by 6, what happens to its area? It becomes 6 times as big. Well, if every rectangle grows by a multiple of 6, the whole area is going to be 6 times as much. Okay, the integral from a to b of f of x dx is the opposite of the integral from b to a of f of x dx. I put this on the board last week. Here's what the rule actually says. Reversing the limits of a definite integral changes the sign. Note, this does not say that if the upper limit is smaller than the lower limit, then the integral is negative. It doesn't say that at all. The integral from pi to 2 pi of the sine of x dx. What is the value of that integral? -2. So if I integrated from 2 pi to pi of the sine of x dx, the value of that integral would be +2. So just because the lower limit is the bigger number doesn't mean you have to have a negative answer. It's a good habit to start taking integrals and rewriting them where you put the smaller number as the lower limit. That's a good habit to be in. It's not always necessary, but this is a widely, how do I say it? A rule that is widely misinterpreted. A lot of people look at this thing and they say, if the bigger number is on the bottom, then the answer has to be negative, and that's not the case. There's nothing in here that says anything about which is bigger, A or B. All this says is no matter what the integral is, when you switch the limits, you'll switch the sign of the value. Okay, the integral from a to b of f plus g is the integral from a to b of f plus the integral from a to b of g. We'll write that as the integral of a sum is the sum of the integrals. Of course, it works for differences as well, that then subtraction. One way you could interpret this is to say that the integral symbol distributes over addition and subtraction. The integral symbol will not distribute over multiplication and division in the same way that derivatives didn't. All right. Intervals can be added or subtracted. If you find the area from A to B under F, and then find the area from B to C under F, add those together, you will get the area from A to C. Is that vaguely familiar? What does it look like? I'm not going to call it that. It does kind of look like the transitive property now that you say that, but a couple of things you learned in geometry are very similar to that, aren't they? For segments, AB plus BC is equal to AC. The measure of angle AOB plus the measure of angle BOC is equal to measure of angle AOC. And the measure of arc AB plus the measure of arc BC is equal to measure of arc AC. Now, this one was known as the segment addition postulate, angle addition postulate, arc addition postulate. Of course, this one is, I kind of fudged on that a little bit. Yeah, you could treat this as the integral addition postulate. The reason this might not be true is if arc AB plus arc BC takes you beyond half of the circle, then this might not be the correct value. All right. But here's a picture of what this is about. If you have function f and you integrate from a to b, and then you integrate from b to c, the total area can be calculated by, get this, integrating once instead, or by totaling the area. Okay. Now, again, I'm only going to bring this up, and I'm not going to show example after example. I only bring this up because I want you to have seen it. This is not something I want you to be using a lot in the very near future. But notice the name, Fundamental Theorem of Calculus Part 2. Oh, I wonder if that has any importance to what we're doing. Fundamental Theorem of Calculus. Part 2, because there's, part 1 is the hard part. Part 2 is the Interestingly enough, if I asked you, have you taken algebra, you'd say, yeah, I took algebra 1 and algebra 2, and pre-calculus is essentially algebra 3. So what's the fundamental theorem of algebra? You'll all look at me like, huh? And if I said, did you take elementary math in grade school? You'd say, I took it for 6 years, and that's called arithmetic. And if I said, what's the fundamental theorem of arithmetic? You'd say, 1 plus 1. You have 6 years of arithmetic, but you don't know the fundamental theorem of arithmetic, and you have 3 years of algebra, but you don't remember the fundamental theorem of algebra. However, you're only going to have 1 semester of integral calculus. You will know the fundamental theorem of calculus when you leave here, both parts. All right, if you have a continuous function with closed endpoints, and capital F is the antiderivative of little f, then the integral from a to b, from f of x dx, turns out to be capital F of b minus capital F of a. Now, you don't have to write that down. It's on that sheet. And you're going to use this so much. This is the second semester equivalent of the power rule. from first semester? You know how continually used the power rule was? Yeah, this will be used so often it will become second nature. And we'll spend plenty of time practicing it. Let me give you an example. The integral from 0 to 1 of x to the 5th dx. So it says what I need is the antiderivative of the integrand. Well, what is the antiderivative of x to the 5th? Turns out to be x to the 6th multiplied by 1/6. Take the derivative of that. X to the 5th. Now, what you do is you say, now I've found the antiderivative, so I don't need the integral symbol anymore. You say, so you write a vertical bar and you put the 0 and the 1 here. Now let's plug 1 in and let's plug 0 in and subtract. So that turns out to be 1/6 of 1 to the 6th minus 1/6 of 0 to the 6th, and that value turns out to be the 1/6 that we were using last week. Let me show you one more example if I can get a new slide to show up. New slide. The integral from 0 to pi of the sine of x dx. So I'm thinking of a function, and the derivative of that function is sine. What function was it? Or is it? What is it? Negative cosine. So this becomes negative cosine of x from 0 to pi. That would be negative cosine of pi minus negative cosine of 0. What's the cosine of pi? Negative 1, and then double negative here, and the cosine of 0 is? The negative of negative 1 is 1. 1 plus 1 equals 2.
So you just take the derivative of plugging the endpoints.
Take the antiderivative.
Is the antiderivative the same as the integral?
What's the derivative of sine?
I didn't ask you for the derivative.
No, I know, but is it the derivative of sine?
Cosine. The answer to your question is sort of yes.
What is it?
A derivative done backwards?
So negative cosine is the antiderivative.
Right.
When do we do it?
Think of the derivative of negative cosine once. What would it be? Sine. Yeah.
But are there like problems?
Pardon me?
Or are there like problems that you're just zero instead of finding the actual
I'm not sure what you mean instead of finding the actual integral.
like
Instead of doing geometry? Yeah. The geometry problems were essentially warm-up to teach you that definite integral means area under the curve. That was the whole goal behind that. Most of the integration you'll be doing will be using this process. And again, I only show you this right now because I don't want it to seem so mysterious as time goes by. We did this problem last week and everybody was saying, hey, where did the 1/6 come from? Well, that's where it came from. Now you've seen where it came from, it's no big deal. The applications of the integral are far more important than this process because, you know, if you really had to find the value of an integral, you'd punch it into your calculator and do it that way.
will we get to a point where there'll be like a function instead of like
Where there will be a what?
like we'll get to take the antiderivative of like a function, like a polynomial?
Yes, we'll be doing that constantly. It doesn't come for a while yet. There will be 1 week where we do nothing but answer problems like this. Nothing. We'll do 100 of them over a 5-day span. And the whole thing will be just find the numerical value of this definite integral. Check it on your calculator, but don't do it on your calculator. Okay, so here's a rule. Again, I don't care if you know this when you leave here today, but just so that it's not a mystery, the antiderivative of x to the n is x to the n plus 1 multiplied by 1 over n plus 1. And how I'll always mention it is add 1 to the power and then multiply by the reciprocal of that new power. The plus c again is the constant of integration, that's not necessary in a definite integral. It's only necessary in an indefinite integral. And you'll get so much practice at this that it'll become as second nature as, what's the derivative of x cubed? 3x squared. So next week I'll say, what's the antiderivative of x to the 7th? Say, oh, that's x to the 8th times 1/8. Add 1 to the power, multiply by the reciprocal of the new power.
Is this gonna be just like derivatives for every different style of function as a different style of?
Yes, yes. He asked a really good question. Is this going to be like derivatives where every different style of function has a different type of antiderivative? You bet. You bet. So polynomials will use the power rule. Trig functions, every trig function is going to have a unique antiderivative. What's the antiderivative of secant squared? Tangent. Now, if I asked you what's the antiderivative of tangent, you wouldn't know that. You don't have that information. The derivative of tangent, natural log, the antiderivative of tangent is the natural log of the absolute value of the secant. And by the way, I've had you do that problem a large number of times. Think about this. Tell me the derivative, d dx, of the natural log of the secant of x. You can do that. Derivative of natural log u is 1 over u prime. So that would be 1 over the secant of x times secant of x times tangent of x, which turns out to be simply tangent of x, right? That was a question that was in the chapter 3 quiz and test. So all of the problems you'll need, you don't know the antiderivative of tangent, but I've had you do the derivative of something and had it turn out to be tangent. Yes, I have had you do those along the way so that they are familiar. Here was a problem from the chapter 3 test. Find the derivative of the natural log of secant of x plus tangent of x. And that turned out to be secant. There was a reason I chose that problem, because this is the antiderivative of secant. But now we're getting way ahead of ourselves, which is a bad thing because today is a day when we're short 5 minutes anyway. We have a lot of time. 15 minutes left. Okay. Remember, a definite integral is just a number. That's all it is. So there's some function out there, function f. And if I drew it between 1 and 5, the area under the curve would be 12 units. And if I drew that same function, f of x, from 1 to 12, the area under the curve would be only 8 units. There's a lot that can be inferred here. Finally, if I drew function g from 1 to 5, the integral, or the area under that curve, would be 6 units. Now, I can take those 3 facts and answer a bunch of other questions, like find the integral from 1 to 5 of 3 times f of x plus 5 times g of x. Get that in your head? Consider the rules, and you have them on that yellow sheet. 2 things come into play. The integral of a sum can be the sum of the integrals, and these constant multiples can be moved to the front. So I would treat this as 3 times the integral from 1 to 5 of f, which is going to ignore all the formality here, plus 5 times the integral from 1 to 5 of g. This definite integral is nothing more than a number. 3 times 12 plus 5 times 8, wait a minute, 5 times 6, gives me 36 plus 30, 66, just like adding set would. So the nice thing about that was, it was intuitive. You didn't know that was the right answer when you said it, but you were pretty confident. You were confident enough to say it. Do you know why this is intuitive to you? Because you've studied geometry. And the rules of geometry are just more basic versions of these. Tell me the integral from 5 to 1 of f minus g. One thing I mentioned earlier, get in the habit of putting your bigger number on the top. So I'm going to switch this to the opposite of the integral from 1 to 5 of f minus g. Now that opposite pertains to the whole thing, right? So it's the opposite of the integral from 1 to 5 of f minus the integral from 1 to 5 of g. So then the opposite of, what's the integral from 1 to 5 of f? 12. And the integral from 1 to 5 of g is 6. 12 minus 6 is 6 with a negative sign in front. Gives me a value of negative 6. It's a good habit to be in. When you see these numbers with the bigger numbers on the bottom, take a second to rewrite the integral with a negative sign in front. Tell me the integral from 5 to 12 of f. Here's what I have. The integral from 1 to 5 of f plus the integral from 5 to 12 of f should equal the integral from 1 to 12 of f. All right, well, the integral from 1 to 5 is 12. The integral from 5 to 12 is the unknown quantity here. I'm going to call that x. And the integral from 1 to 12 is given as 8. I'd say x here is negative 4. All it is substitution. All right. I'm going to give you this definition today so that the next time we talk about it is the second time we've talked about it. You're not going to want, there are going to be a bunch of average value function problems in your homework today. Those are the ones I would skip and save for Thursday. So I'm going to put an assignment up today, and I'm going to give you the exact same assignment Thursday. Get as much of it as you can done today. Save the rest for what goes on Thursday. So average rate of change of a function is nothing more than slope of a secant line. Average value of a function goes like this. To get the average value of a function on the interval from a to b, you'll integrate it from a to b, and then multiply by 1 over b minus a. It's as easy as that. Yep. That's a definition you're going to want to commit to memory. Here's what it really says. If you took the region and converted to a rectangle with a base length of b minus a, the height of that rectangle would be the average value of your function. The region is converted to a rectangle, but you keep the base length as b minus a. The height of the rectangle would be the average value of the function. Let's see what we have here. All right, I'm going to stop right now. I don't want to quit everything. I just want to get the assignment up here for you. And then I just want to go one little bit further on this lecture.